This problem is asking for the probability that either M or C occurs. So unite all the probability that M occurs, the total for M, and all the probability that C occurs, the total for C. But when doing that, this part gets counted twice. So we have to make sure to subtract the intersection there that got double counted. And that will be your final answer for the probability of M union C. For number 38 is the probability that M will occur if we're given or if we know that C is occurring for sure. So you're really only looking at this row. The rest of the table, pretend it's not even there because we know C is what happened, because that's what we're told after the up and down bar here. Whatever comes after that is what happened. So the total probability that we have to work with is the 0.049, because we're only looking at C. That's the total. And the chances that M occurs out of that 0.049, M accounts for 0.042 of that. So reducing that fraction will give you the correct answer. And then for number 39, it's similar. Our world is again reduced to just the C row. We're given that C happened for sure. And so what's the chances that the complement of M happened? M not. So again, the bottom's 0.049. That's the total in the C row. And M's complement makes up 0.007 of that. So reduce that for your answer. Alright, for number 60, here's the information we're given. And here's what you have to do to test independence. Okay, if we're trying to find the probability that two events happen, so in this case, it's the medicine works, it's effective, and you have the side effect. If they're independent events, you can just multiply the probabilities of each of them together, and that'll give you the probability that they both happen, that both things happen. And so in this case, we can just test that out. So the problem tells us that 30% of the time, both of them happen. And then is that equal to 0.75, the probability the medicine's effective, multiplied by 0.4, the probability of a side effect? And in fact, it is. So because the probability of both of them happening is equal to the probability of each of them just multiplied together, that proves independence. So these events are independent. A lot of events aren't independent, and this is what we usually have to do if events were not independent. It would be an equation like this. Because a lot of events in life, for example, when the medicine works on your body, that could reduce the chances of a side effect. And then when a medicine doesn't work on your body, maybe that increases the chances of a side effect. One event occurring usually alters the chances that the other event will occur. And so normally, if they're not independent, to find the probability of two events, you have to multiply the probability of one event, and then multiply by the probability of the second event now that it's been altered or changed because that first event happened. Okay, so we're still doing probability of it being effective multiplied by the probability of the side effect, but this probability is probably changed or altered based upon what's already taken place, based upon the medicine being effective. So this is what you would typically do for just a general problem. But anytime they're independent, you can just multiply the probabilities together without worrying about the conditional probability. And to wrap back to where this problem started, anytime you're testing for independence, this is the test you need to run. Just multiply the two probabilities together and see if they are equal to the probability of both events occurring. For 19 on page 543, I'll help you get it set up. So there are two outcomes here. X stands for your outcomes. So one is you play the game and you lose. In that case, you're going to lose $1. It costs $1 to play. The other option is you pick the correct number and you win. In that case, they give you $500 back, but you paid $1 to play, so you're going to come out $499 ahead. So those are your only two outcomes. You're picking between 1,000 numbers. You can pick between 000 to 999, which is a total of 1,000 numbers, and you get to pick one of them. So the chances you lose, there's 999 losing numbers, and there is one winning number. So use that table to figure out the expected amount to win, or the expected value from this probability distribution. For 27 through 30, I've just created a similar problem, and I'll walk you through how to do these. The question says determine whether the distribution is valid or not. All you need to do is focus on this row that contains the probabilities. To be valid, there are two things that need to occur. The probabilities should add up to 1 or 100%. Alright, so all of these should total 1. If they're less than 1 or they're more than 1, it's an invalid probability distribution. The other thing is the probabilities should all be between 0 and 1. Every probability has to be between 0% and 100%. So if any of these were a negative number, or if any of them were 1.6 or 2.9, some number bigger than 1, that would be another case of an invalid probability distribution. So just check for these two things. If both of these occur, then this is a valid probability distribution. For number 27 and 29, they're talking about social security numbers and postal zip codes. So a social security number has 9 spots in it. To figure out how many are possible, you need to know the number of choices for each spot. So the first number in your social security can be anything between 0 and 9, any of those digits, which is 10 choices. The second number in your social security also has 10 choices, anything between 0 and 9. In fact, all of these spots, there are 10 choices for that spot, any number between 0 and 9. And so then to find the total number of options, you just multiply the number of choices for each spot. Multiply them together. So in this case, you're going to do 10 times 10 times 10, 9 times. And in fact, it's the same for number 29. Instead of a 9-digit social security number, we're talking about 9-digit zip codes. And for your zip code, you have that same situation. You have 10 choices for each spot. Any number between 0 and 9 gives you 10 options. For number 65, page 559, the key is there are 9 total cans of Coke, or of pop, and we are selecting 3. So for any of the questions A through G, your bottom number is going to be 9, choose 3, because that is the total number of selections you could make if you're selecting 3 items out of the group of 9. And then the top part is going to be how many ways can you do whatever the question's asking for. So I think I'm at number D here, 2 Pepsi and 1 Coke. So how many ways can you select 2 Pepsi? Well, there's 5 Pepsis, and you're going to be selecting 2. So that's how many ways you could get the Pepsis, and then multiply that by the number of ways you can get the Coke. There is 1 Coke, and you're going to be selecting 1. So all A through G will follow that similar pattern. For number 2 on page 565, here's the situation. They tell us there's 5 defective, which means there has to be 19 good tiles, and we're selecting 3 at random. So there are only 4 options. We can select 0 defective and 3 good tiles, or 1 defective, 2 good, 2 defective, 1 good, or all 3 defective and 0 good. And to figure out the probabilities of each of these, it's pretty similar. The total number of options, if you're selecting 3 tiles out of 24, for each of these is 24 and you're choosing 3. And then the top part is the number of ways you can do whatever is written in the parentheses here. So for this one, there's 5 defective and we're choosing 0, and multiply that by, there's 19 good tiles and we're choosing 3. And follow a similar pattern. So number 2, the actual question is, what's the chances that the batch is rejected? The company will reject the batch if any of these 3 situations happen. If there's 1 defective, 2 defective, or 3 defective. Because if they find a bad tile, they are not going to ship that batch of tiles. So you can figure out these 3 things and add them together, and that's the probability that the batch will be rejected. Alternatively, the opposite of all of this, the only thing left out is just this one. So you could just figure out the chances that there are no defective, which means the chances they accept the batch, that they actually like this batch of tiles and use it, and to do 1 minus that, and that'll give you the chances that they reject the batch. So either do this or work all 3 of these out and add them together. For 29, here's how it's set up. There's basically 15 people and we're selecting a group of 4. So the bottom part of your equation is always going to be the 15 and we're choosing 4. That's how many different groups of size 4 we could possibly get. And then the top part is the number of ways you can do whatever it's asking for, whatever's in parentheses here. So 3 women and 1 man for part A. Well, there's 4 women, we'll be choosing 3 and multiply that by the number of ways to get 1 man out of the 11. For part B, you're doing 0 women and 4 men. So out of the 4 women, we're choosing 0, and then out of the 11 men, we're choosing 4. Multiply those together to count the total number of ways you can get groups like that. And then the part C, at least 1 woman. So there's 4 options for at least 1 woman. There could be 1, 2, 3, or 4. That would be groups with at least 1. So you could follow this similar pattern, figure all these out, and add them together. And that would give you the probability of at least 1 woman. Or what's the only other option for at least 1 woman? Or sorry, what's the only other option for the cabinet? Well, we've done 1 woman, 2 women, 3 women, 4 women. The only other option is 0 women. So if you just did 1 minus that, then what you'll have is the same thing as doing all 4 of these and adding them together. Alright, for number 5, page 572, I refer back to number 1. You just need to use the binomial formula and plug in 6 for K. There's 10 trials or 10 kids, so N is 10, and then the chances or the probability of what we're looking at is 70%. So plug those numbers into the binomial formula. For 5, it's the same thing. You're going to use the binomial formula, but it doesn't say exactly 1. It says at least 1 kid who lived with their parents. So you'd have to do this one, and I will write them out here. That would be at least 1 kid. Add it to, if there's 2 kids, that's at least 1. Add it if there's exactly 3 kids who lived with their parents. That's at least 1. All the way up until you get to 10 out of 10 kids, because that would be at least 1 person living with their parents. So you'd have to do 10 things and add them together. Or you can use the fact that the only thing left out from all these choices, either 1 kid, 2 kid, 3 kid, all the way up to 10 kid, the only thing that we've left out is the complement, 0 kids living with their parents. So figure out that probability and do 1 minus that, and that'll give you all of these things added together.